DDPMs. So now inference with DDIMs. So what is inference? As we know that it's simply sampling. So inference is sampling from the reverse process, right? That's all. It has been always sampling from p theta of xt minus 1 given xt. This is exactly what inference is all about. And what is this? By definition, we have defined this to be this particular thing. See, now if we have trained a DDPM, we have this as theta star, because we have already tried this. Okay, now let me also write the definition of mu theta, so that we have all of it in one place. Because of this, the sampling procedure is the following. So we want xt minus 1 to be equal to so how do we sample? We simply sample from this particular distribution. How do you sample from this particular distribution? We know that this is a Gaussian distribution here. This, please recall that this distribution has been defined to be this way, which is a Gaussian distribution. All we need to do is that we need to replace x naught here by mu theta. That is what we need to do, and we need to sample from. Okay, so let me just copy this as well, so that we have the context. Okay, so what we need to do is sample from this distribution. Now instead of x naught here, we need mu theta, right? Because that is how we have defined our p theta star. Instead of x naught here, we just have this mu theta. So wherever we see x naught here, we need to simply replace it with mu theta. That is what we need to do. Let us write this as mu theta star, and this is also equal to mu theta star, right? We need to sample from this particular Gaussian distribution. And how do we sample from any Gaussian distribution? We simply start from putting all the above together. Sampling from p theta star of xt minus 1 given xt is as follows. So we know that it's a Gaussian distribution, right? How do we sample from a Gaussian distribution? As usual, we start with some z, that is normal 0 1. Okay, and we take that, and we need the variance to be equal to sigma t squared. So therefore we'll write this as sigma t squared times z. This is the scale that we are doing, and we just shift it with the mean. So what is the mean? The mean is equal to this entire thing. This is what we will write down. So the mean is equal to, so my xt minus 1 will be equal to root of alpha t minus 1 times mu theta star. So what is mu theta star? We have written mu theta star to be this. Take that down. Okay, this is the mu theta star. We have the other term as well. So this is a very long equation. So let me write this as sigma t squared times z. Okay. These what is the mean has the mean itself has when we wrote this term. What about this second term? Let me write this second term as well. So we'll take this. We take this term. So the mean, I'm writing this, the mean, this is plus this particular term, and this is multiplied by xt minus root of alpha t mu t star divided by 1 minus alpha t. What is that equal to? Just look what that is equal to. So this implies that xt minus root of alpha t times mu theta star divided by root of 1 minus alpha t, this is equal to the predicted epsilon, right? Predicted epsilon from the network. Just rearranging the terms. So whatever the term that was multiplying this particular term now will be written as epsilon theta star. So this is epsilon theta cap, which is the predicted. I'll put a star here because we have already predicted. This is a learned neural network, and the final term, which is the Gaussian thing, we'll write it that way here. This plus sigma t square times c. So this is the sampling equation for a DDIM. So note that with different sigma t's here, so we have a sigma t here, right? So different sigma t's will make you sample from a different forward process. As I said, no, the forward process is parameterized by the sigma that we have. So we choose a different sigma, we have a different forward process, is what we saw. Okay. Now what happens is here we have given a generalized sampling procedure for all these family of models, okay, with different sigmas. So the sigma t represents the same sigma that we have here, which we used to define a family of the generative models. In fact, every family can be written as, I don't have to write it as a scalar, let me write it as a vector, because this is different for different times, right? Because we have time indexed vector sigma, so at every t we have a different value of it. That is why I've been writing as sigma t. So every sigma t, a positive vector sigma t, will give you one family of, or one forward process, and this is the sampling procedure for it. Okay, I hope that this is clear. I mean, this looks a little complicated, but it is not. I mean, all we are saying is that by training one DDPM network, we are training a whole bunch of family of non-Markovian processes whose sampling procedure is given by this particular formula. Okay. Now, what is interesting is when sigma t, which is the family of parameterized vectors that we have taken, is given by this particular formula, root of 1 minus alpha t minus 1 divided by root of 1 minus alpha t times root of 1 minus alpha t divided by root of alpha t minus 1. If you take this particular value of sigma t the above forward process or above random process reduces to DDPM. Okay, so which means that DDPM is a special case of these family of models with sigma taking a particular value. That means that while you are training a DDPM, you are also training a DDPM, of course, and you are training a much larger family of models. So that is the idea. This is another special case. Okay, so when sigma t is equal to 0, we have said that the sigma t can be any non-negative real vector, so it can take a value of 0 as well. If that is 0, then what happens is this term completely vanishes, right? With sigma t equal to 0, the sampling procedure has the following form. So x t minus 1 will be equal to root of alpha t minus 1 times this entire first term remains exactly the same. So let me write it down. X t minus root of 1 minus alpha t times epsilon theta cap divided by root of alpha t. So note that this epsilon theta cap, I'll have to actually write a star here. This epsilon theta cap star is coming as the output of the neural network. Now remember that our neural network, the DDPM neural network, takes xt and t as input and gives you an epsilon theta star as output, right? So that remains the same. So this is the first term. The second term will be plus 1 minus alpha t minus 1, there's no sigma here, root of this times epsilon theta cap star. Okay, so note that this is completely deterministic. The above sampling procedure is deterministic. So what does this imply? This implies that the only randomness is from x capital T, which is a sample from normal 0 1. So just like a Gyan, right, where you start from a particular you sample from a normal 0 1 and you pass it through a generator and it will give you one particular generated data point. No matter how many times you pass it through it, you just get the exact same data point. But in a DDPM, what happens is you sample one particular data point from xt, you run through the reverse process. If you run through the reverse process, every time you get a new generated data point. Okay, but in a DDPM, in a DDIM, so this is this particular case, right, with sigma equal to 0, sigma t equal to 0, the above model is called DDIM. Okay, because this is an implicit model in the sense that there is no stochasticity while we are sampling, other than the stochasticity that is coming from the last latent variable or the input noise. So start with some input noise and run through this particular backward process. If you run through this backward process, every time you fix this xt, you are going to end up getting the exact same input, exact same generated point x naught. Okay, so now this also implies that the forward process in DDIM the forward process in DDIM with sigma t equal to 0. So a DDIM is the case when sigma t equal to 0 is also deterministic. Why? Because the reverse process is deterministic. We also have the forward process to be deterministic as well. Now, what does this mean? This means that the above implies that a DDIM has a unique invertibility. Which means that if you start from an x0 and run the forward process of a DDIM, okay, you will get a particular noise xt, right? And if you run the DDIM process again with the exact same x0, you will get the exact same noise every time you run the DDIM process. This is also called DDIM inversion. So DDIM inversion is simply the process of starting from a given image and running through the forward process of a DDIM to get a particular noise vector xt. So that is called DDIM inversion. Now, what is done in practice to solve the problem of image editing that I just that I mentioned in the beginning of the lecture, which is that suppose you start from an image of let's say a tiger in a particular forest, and you want to change that tiger to lion or rather elephant without changing anything else. What is done is take that particular image, okay, and run it through the forward process of a DDIM. If you run it through the forward process of a DDIM, you get a particular vector, latent vector or a noise vector corresponding to this particular image. Okay. Then what is to be done is that we know how to condition these models using text. So what is to be done is that you change the text conditioning by saying that now generate the image corresponding to an elephant being in this exact same scene and run a conditional DDIM's reverse process given by this particular equation. Okay. Then what you would get is the exact same image with everything else being the same, but that particular tiger's image is replaced by that of elephant, because that is the way the text condition has been put. Now, suppose you didn't have a unique inversion, what would happen is you can still change the input text prompt, but what will happen is everything else in the background does not remain exactly the same, because the latent vector or the noise vector that we have obtained by running the forward process of a DDPM will be different even if you give the exact same image. But here in a DDIM, given a particular image, since the result of the forward process would end up giving the exact same noise vector every time, then a simple thing for editing any image would be to start with the given image and get the corresponding output noise vector corresponding to this particular image, and change the textual prompt for this particular image and run the reverse process again. So that would produce the exact same image that we started from with the particular edit that we have suggested using the text. So that is one of the biggest advantages of using a DDIM because it can be inverted with the deterministic forward process. So because this process is also non-Markovian in nature, the number of time steps capital T that one would need in generating these images is much lesser compared to that of DDPMs. So we have solved both the problems of non-unique invertibility and the slower nature of sampling using DDIMs. Again, let me repeat, the fundamental idea is to define a family of parameterized non-Markovian processes which has the same marginal as that of DDPM, so that training one DDPM is equivalent to training all these family of models. So now what changes is the inference process. So by changing the inference process as given by this particular equation, you will be sampling from different non-Markovian processes. One particular special case is when the sigma t is equal to 0, in which case both the forward and the backward processes becomes deterministic. Okay, so that is the summary of DDIMs, and this would take us to the end of diffusion models. Now, there are enormous amount of applications that people have looked at on DDPMs and DDIMs and so on. Since this is not an application course, I would refrain from going into those applications. Interested readers may go up and look up the literature to see how DDIMs and DDPMs arise. By the way, today's state of the art is using DDIMs on latent spaces. So all the image generation softwares that you see with all the commercially available software such as GPT and Gemini and so on are mostly using DDIMs while generating and editing the images. Okay, so this takes us to the end of diffusion models. We will revisit diffusion models when we look at the language models, the autoregressive language models. So people have tried to use diffusion models for sequential data as well. Most prevalent application of diffusion models is in image generation. People have not, till very recently, there have been very little efforts in using diffusion models for sequential data generation. But now, very recently, diffusion models are being used for sequential data generation like text as well. We will go to it when we look at the large language models from the context of autoregressive models. Okay, so the next topic that we will be looking at are autoregressive generative models, which are also called the large language models, and we will look at different architectures such as transformers and different ways to train them and align them. Thank you.